Hello. Today, I would like to discuss a topic that I've never discussed before. It's about quantum computers based on an MITx Pro course that I took in quantum fundamentals. And I want to talk about designing quantum algorithms in relation to classical computing. Special thanks to professors in MITx Pro courseware, Dr. Isaac Chung, Dr. William Oliver, and Dr. Peter Shore for the Quantum Fundamentals course. And also, I would like to thank Johns Hopkins University and Dr. Mike Levine for the computer organization course that gave me the knowledge required to create a fundamental overview of the relation between classical and quantum computers. uh, and the whole purpose of this is not to go too into depth about in quantum computing or too in depth in classical computation, but to give a general overview of the two technologies and the potential for the quantum software engineer role to evolve, and what is the mindset that should that is required for the quantum software engineer as opposed to the classical software engineer. So, quantum computing bandwagon. Quantum computing has gained interest in many groups seeking to discover a quantum algorithm with a potential to outperform classical computation. And the question is, how do you develop an optimal quantum algorithm? The fundamentals of computational theory, based on MITx Pro, Dr. Isaac Chung from MIT discusses computational theory and mentions the theoretical possibilities of quantum computers outperforming classical computation. He says that in mathematical theory, a quantum bit has an exponential advantage over classical bits. This principle relies on the quantum superposition state. He also mentions just because there exists a possibility of a quantum algorithm to outperform a classical algorithm does not necessarily mean that a classical algorithm cannot exist that can possibly have the same advantage, not over quantum. This is actually a typo. This is that cannot that a classical algorithm cannot exist that can have the same advantage. So this is just computational theory, fundamental. So the question is, how should you develop an effective quantum algorithm? In order to answer this question, we have to understand the context of quantum computing to classical computers. Let's talk about the relation between quantum bits from a perspective of classical computing, particularly how a classical assembly language compares with the quantum assembly language. So, the classical assembly, ASM, in classical bits, basically it assembles machine code. And the machine code you have is it's a text of ones and zeros. To be displayed right in front of your face is just a text of ones and zeros that is processed by the processor directly as ones and zeros. So the question is, how exactly do ones and zeros break down into functions that computers operate? That's the whole question. So how can you make sense of ones and zeros? So here, the classical assemblers will assemble machine code into a processor and basically run it on the processor. In basic overview, how exactly does that work? The assembler processes line-by-line execution in 32-bit words. So, giving a example of this, I think I need to take this out. But let's give an example of this. These array of 32-bit instructions represent a Mips assembly function that can be represented as human-readable code. For example, a 32-bit instruction, this value 100000, and this entire 32-bit instruction. Let's take a look into how that breaks down into a function that we understand. So how does this value of ones and zeros represent a function that a computer will operate, like perform? So let's take a look into the instruction format of Mips assembly. So you have three different general function types: R-type, I-type, and J-type functions. And this will format a template for an instruction, a machine code instruction to run. So the first 6 bits of the instruction is known as the opcode. The second 5 bits, the second 5 bit is known as a register value and is expressed in 5 bits. So we have a so we have a RS register, an RT register, and an RD register. Each one of them are 5 bits. We have a champ value, which is basically an offset, which will offset the bit after computation. That is stored as a 5-bit value. And finally, we have a 6-bit function code. So let's take a look into the Mips reference sheet. So we have the instruction format. And let's say I want to express a function. For example, let's do a simple add function for demonstration. We take the add function, we find the opcode, which is this value, 100000, and we will take this opcode and we will format our instruction type. So the first 6 bits of the opcode is going to be that value. The function value, the opcode and function value is currently the same for this, is going to represent the R-type function. So opcode, function code, filled. And if we want to store that value into a register, we have optional register in Mips. For example's sake, we will use a temporary register, and we're going to take the values of T0, T1, and T2 and place that into a function. So basically, this operation boils down into a format where you're going to perform an add function of T1 plus T2 and store that value in T0. So that is a 32-bit Mips assembly function or instruction. So, okay, let's move on. The add function, broken down into classical logic gate, represented as a function that can scale by cascading per size of input registers. Classical bit computation. So the representation of the add function is in XOR gate. So you have an input A and B. So output 1 is A XOR to B. And the XOR gate truth table is basically if you have a 1 and a 0, the output will be 1. If you have a 0 and 1, the output would be 1. If you have a 0 and 0, the output would be 0. And if you have a 1 and a 1, the output would be 0. And the other part of this add function is a AND function that will go into output 2. And this is basically a value that will be stored as a carryover. So the AND function truth table, 1 and 1 equals 1. So you take the value of, let's say, 0, 1 added to 1, 0. So 0, 1 is equal to 1, 1, 0 in binary is equal to 2. So we know that 1 plus 2 is 3, and the binary representation of 3 is 1, 1. So A and B, 0, we have, let's say we have, 0, 1 going into A and 1, 0 going into B. So the first bit value, 1 plus 0. 1 plus 0 XORed together the output would be 1, and the carryover would be 0. So the first input value is going to be 1 over here. The second input value, let's say, is going to be 0 and 1. 0 and 1 output would be 1, and the AND carryover of 0, 1 is going to be 0. So you have the value output 1 and 1. So that's going to equal 3. Okay. Let's talk about classical optimization. Classical optimization is a very simple general description, means that there is a mathematical theorem where a complex operation can be broken down into a more simple operation to yield the same result. Very simple example, omitting all complexities, looking into De Morgan's theorem. De Morgan's theorem states that if you have a value of A or B inverse, A or B inversed is the same as inversing A and inversing B. And similarly, if we have a function A and B inverse, A and B inverse is equal to A inverse or B inverse. So this value expressed, this theorem basically means that it's an identity. If we have AB inverse, that is also equal to A inverse or B inverse. So the representation of that circuit diagram, for example, we have A inverse gates to A and B inverse, or together we will have 3 gate operation that yields A inverse or B inverse. Okay, this same gate will yield the same truth table as an A and B NAND gate. So a NAND gate is basically an AND gate with an inverse at the end. So a NAND gate can, the output of an AND gate is the same as the output of an inverse A and inverse B into an OR gate. So using De Morgan's theorem, we can break down a 3-gate logic function into a 1-gate logic function. So classical optimization. Continued. In classical computers, the instruction, 32-bit instruction, that I previously mentioned, does not necessarily mean that only 32 classical bits were used in computation. Rather, this is a representation of a function to execute by the processor to generate the logic gate operations to compute. So a little bit wordy, but basically it means that this instruction basically tells the processor what function to run. The actual values of the registers is a reference pointing to a memory location of the actual data store. So the values of, for example, T1, T2, and T0, these are actually a reference to a memory location where the actual value is stored. So that's basically what I mentioned here. For example, data stored in register T1 may hold a 32-bit integer value for the actual computation. So the actual number of classical bits used for classical computation may be greater than the actual Mips instruction. This is important because it explains the difference between classical assembly language and the quantum assembly language. Moving forward. So in reality, we are loading memory, communicating between the processor and RAM. The RAM is also able to load information from storage. So that is what we currently have with classical computers. We have a CPU unit, we have a memory, we have a storage, we have I/O operations and other hardware that can talk to the RAM, talk to the CPU, and we can exchange data from many locations. So bits are being transferred in and out. The I/O device into the memory, loading into memory, and then memory is loading and crunched into the CPU. Classical computation. Quantum assembly language and QASM. Quantum assembly is completely different from classical assembly. It actually performs computation on qubits at a much granular level compared to classical assembly. Challenges facing quantum software engineers versus classical software engineers involve completely rethinking computation. Understanding the qubit. Expressed in vector notation and allows three possible states: classical 1, classical 0, and a variable quantum state. So we see the classical qubit in a Bloch sphere, and we have a ket of 0, ket of 1. Spin up represents ket of 0, which is a vector notation of 0, and spin down means ket of 1, which is a vector notation of 1. So the bracket notation is special in quantum computing because it can represent vectors rather than classical bits. It's a little bit different in computational mathematics. And we have a superposition state of ket of 0 plus ket of 1, which is, and the square root of that, which can represent the superposition states. Not going into any complex details, let's just take it as is and keep it simple. Quantum bits can simultaneously express 4 prime numbers at the same time with only 3 quantum bits. This is just an example. The first two qubits are in superposition states, which means that they can be, the first two qubits here can be represented either as a 1 or a 0, and the third qubit is spin down. So we can see that if we put 3 qubits, the first two in superposition state, and the last qubit is spin down, we'll see that the output of that can represent possibly 4 prime numbers at the same time. It can be 1, 3, 5, or 7. Okay? Quantum bit versus classical bit. The first obvious advantage of quantum bit compared to classical is that it allows a third possible outcome, which is true randomness. So the challenge, how can we exactly express computation between quantum bits and classical bits? For example's sake, let's say we replace computation of all classical bits in modern computing into quantum bits. What exactly can we accomplish? So what? We can replace classical bits in assembly instruction into a random value. Simultaneously express 2 functions at the same time. Or we can simultaneously represent 2 numbers at the same time in one instruction. So what's the advantage of that? Absolutely nothing. So what exactly is the advantage of quantum computing? So this is a good question. So the whole idea of this is to explain basically that we cannot take quantum computing and compare it with classical. We have to completely rethink this approach because we cannot try to fit quantum assembly into what we have in classical. And to understand what quantum function is, what QASM is, what quantum assembly is, we have to compare it with the classical assembly language and understand exactly what's going on, the inner works. And I decided to create this presentation not to make things too complicated, not to make things too wordy, but to get a general sense of the two assembly languages. Okay. So, quantum and classical logic gates. We have classical logic gates and we have quantum logic gates. We will see that quantum gates allow more operations compared to classical. The quantum advantage. So the advantage of quantum computing is clearly optimization. There can exist a function represented by quantum bits and quantum gates that surpass the ability represented by classical bits and classical gates to optimize an algorithm. Basically, if we want to take a classical operations and we want to optimize it, we have more availability to represent that algorithm with quantum bits than we had previously with classical logic gates and classical bits. So quantum gates, quantum bits gives us an array of options to work with to optimize a classical algorithm. So the quantum advantage of that is optimization, that there is a potential optimization that can exist between quantum functions compared to classical functions. So the quantum challenges. We don't currently have quantum hardware to support processing, memory, or storage that can mimic the same functionality of classical computers. But that does not mean that the fundamental operations broken down by classical computers into classical logic gates cannot be represented in an optimal function provided by quantum operations. In other words, there may possibly exist a quantum function that can significantly outperform a classical existing function. And whether or not a potential Q memory or quantum storage will exist in the future, the operation of quantum computation's advantage can still be recognized by optimizing a classical solution. Fundamentally, a quantum processor's job will be to optimize a classical computation. So I want to end this, and I want to make this as brief as possible, and just answer one question. Can you simulate AI algorithms with quantum computers? The answer to this question is an answer to all questions. Any algorithm can potentially be optimized by a quantum computer. My purpose of this demo was to explain exactly how to think quantum algorithms. There's a typo there. However, if you are thinking that you can take a Monte Carlo simulation, for example, using a forward-backward Euler algorithm and optimizing that solution, well, fundamentally, you will take that complex algorithm, generate a compiled classical logic gate simulation of that algorithm, and try to optimize that function into a quantum bit to quantum logic gate simulation. That is the challenge, and in order to effectively do this, we need to operate on a compiler language that can break down machine code into a series of simulated logic gate operations, and then try to optimize that solution. However, a better fundamental approach would be to take the mathematics of the AI algorithm, created a bit-by-bit operation on small numbers, and find a quantum solution of the same algorithm. So that is the whole idea of quantum software engineering. What are the challenges of quantum software engineering? Thinking about classical computation and how to mold the lines together. So I see a lot of I don't know how to explain it. Like I see a lot of bandwagon quantum fan clubs out there that talk about simulating AI algorithms, and they draw these diagrams about an approach and etc. But the thinking behind it has to be is not the it's not the solution to, like, for example, an AI challenge. If you're thinking that you're going to take, let's say, the function of a forward Euler algorithm, like, you're trying to take the path, the direction of a data, and try to simulate that data for the next data plot in X direction, in the graph, and you're trying to find the solution going down that way. You will fundamentally, in classical computers, represent that as a classical function, right? That classical function itself in classical computing will boil down into logic gate operations to represent that function. In order to apply quantum computational advantage on that algorithm, you have to take that classical gate function of the logic gate simulated for that function, and then try to optimize that solution using quantum gates. Basically, the whole idea of quantum computers is this concept of optimization. So where can you find or convert logic gate operations existing in classical computers, and then reformat that into a quantum template that has a significant optimized performance enhancement to that solution? So that's the whole idea of thinking quantum algorithms. It's completely different. and it may be creative because I mean, from my understanding of it, there's no identity that says that this algorithm is equivalent to this algorithm in quantum, or this whole series of cascaded series of algorithms can be broken down into a iterative approach to simulate a fundamental optimized quantum solution. This is the whole challenge in quantum computing, that the quantum software engineer will have to find that solution themselves, and it's still in the field of research and development to find a solution and then test the solution to see is it truly optimized or not. So that's my the basic thing I wanted to talk about in this video. I've never talked about quantum computing before, um, and yeah, I mean, I'm learning about it more and more, um, and I'm interested to see the future of the technology. But I'm also evolving my knowledge into the direction of the foundation of classical computation, the classical cybersecurity algorithms, and understanding and evolving my knowledge more in that direction before I explore like something like quantum computers. So yeah, yes, I just wanted to make this video to give a little bit of insight from my understanding of quantum computers as well, and just maybe contribute to some of the thoughts behind it, developing quantum algorithms. And from my understanding of the MITx Pro course, I've been trying to really dig my head into the technical understanding of the quantum software approach, like really fix my head into quantum software development rather than underlying working with the hardware, the system, and stuff like that. And so that's a challenge that I saw, and I was trying to find and try to understand exactly how quantum assembly language compares to the classical assembly language in classical computers. And that's all for today. Thank you for tuning in.